Project management problems often, although not always, involve a certain amount of drawing. Definitely these old exam questions here that we're starting out with are a good case of that. Let me show you what I mean. Consider the project information in the table below. Oh, there's a bunch of activities. Oh, each one of the activities is going to take a certain amount of time. Oh, there's some immediate predecessors. And it actually says here, draw and analyze the project network diagram. So we are definitely going to have to do that for this particular problem. That will be the first step. Though, remember, from the project management chapter, there was really two different techniques in project management, PERT and CPM. This is a CPM problem. You can tell because there is only one reading for how long each one of the activities is going to take. That tells you it's a CPM problem. Anyway, I digress. We're going to have to draw this network. Now, when you're drawing project networks, highly recommended get a pencil, even if you don't normally work in pencil. I remembered to bring one. Have plenty of room to work. How do we draw a project network? We draw the start of the network first. We draw the start of the network first. We look on the information who doesn't have any immediate predecessors. These are, I see A, B, and C. These are the activities that, if you were actually working on this project, they are options for starting on right now. So from the start, you could go on to do any of those. All right, now what do? Now we keep adding tasks to the network in a relevant fashion. I noticed that D, for instance, has A as an immediate predecessor. Oh, okay. So D could go somewhere like here. Then, whoa, E, F, and G all have B as an immediate predecessor. Okay, I think I left enough room, but that's why it's nice to first kind of sketch it out in pencil. In case I didn't, because I need to stack these in here, E, F, and G. Each one of them, when you're done with B, it's an option. You could go on and do that activity. Okay, I'm working my way down the list. H has C as an immediate predecessor. Where's C? Okay, C's down here. It needs to be then connected to H. I'll just sort of put it at the bottom of the stack, but be very careful who it's connected to. I only have two left. I has G and H as immediate predecessors. So wherever I draw I, it has to be connected to G and H. Here's I, connected to G, connected to H. And J has D and E as an immediate predecessor. I could put it here. That worked out well. And then just connect it, D and E. That was a D and a P. You say, oh, okay, so you're done with the network because you're done with the list. We are done with the network. All good project management networks have a start, and we remember they have a finish or an end, whatever you want to label it. Because the start represents we started the project, and the finish represents yay, we're done, we can be paid for it, or whatever. Now, who gets connected to the finish? Any square on here that had arrows pointing at it, for instance J, but no arrows leaving it, gets connected to the finish. And you say, well, that's obvious because those two are like at the bottom of the list. They would be at the finish. But notice that's not always true. F also gets connected to the finish here because before I drew that arrow that you could essentially find your way into F, but you couldn't find your way out. Okay, there always has to be a way out, so to speak. Now, I just scratched those in pencil because I wasn't sure as I did it if that's exactly where I wanted to put them. Now I can, if I want, be a little neater. Start. I'm going to kind of ink these in so they're a little clearer. That is A. Oh, right. And I'm going to turn them into tables to store all that other data that I know I need in a CPM problem. Let's see. That's B. This one is C. Then D, and carefully draw the table lines. Notice in drawing a network, always draw arrowheads. You say, yeah, but it's kind of obvious. You're going from left to right. Believe me, depending on the problem, it is not always obvious what the direction of the relationship is, but the arrow tells you. From this task, you can go on to the next task. Almost there. Inking it in. Got a long arrow here that connects F to the finish versus I to the finish versus J. Oops. Better ink those in. And let me make the finish a little bolder. All right, now we're actually all set to work the CP/M problem. And you say, okay, great, now let's get the numbers going and let's do those early start and early finish times. Yes, definitely we will, and we need to answer all the questions. Just a little note, though, on exam writing in general. If there is a large-scale scenario like this one in which you've got to do a multi-step analysis, if there are any questions on your analysis that are data interpretation, meaning that you don't actually have to complete the entire analysis to answer the question, I'll put them closer to the front. I generally always try to do that. Now you say, well, okay, fine. What's this got to do with this problem? If you're running you're running short on time, you know, you only have 10 minutes left in the exam, and you realize, oh no, this is a CP/M problem. This is going to take forever. Wait a minute. Check the early questions, because, for instance, we just went through and drew that whole network, and we haven't even done the numbers yet. I want to point something out. If you were to start on this project, which activities could you potentially start at the very beginning of the project? I didn't even have to do that to answer this, because that's just asking who doesn't have any immediate predecessors. That's all that's asking, which means that without doing any work, you just look at the table and answer that one. Actually, you can answer this second question without doing any numbers. You do need the network. It's asking for which of these are paths through the network. Oh, okay. Let's take a look at this network up on the screen. A path is any complete route from start to finish. So you really just want to test them one at a time. I'm looking at A, B, F. Okay, from start, I can definitely get to A. From A, though, can I get to B? No. Mark it off. False. Okay, B, G, I. From start, I can get to B. Definitely. Okay, from B, I can get to G. Yeah, definitely. And then from G, can I get to I? Yeah, definitely. And last test, from I, can I get to the finish? Can I get out? Yes. Oh, that one, definitely. Da-da-da. That one true. But wait a minute, what about C, D, J? Well, from start, I can get to C. From C, I can't get to D. So it's really only that one right there. So 2 only is a path. Now, can we do anything else quickly? How much time will be required to complete this project? No, that won't be quick. We have to do at least the early start, early finish times. Okay, so, oh, wait a minute, which means we need to finish filling in the data, because this little box is where we can store the duration of each one of these. And we don't have to keep looking at the table. Let's see, A is 11 days long, B is 10 days long, C is 8 days long. I'm just copying data is all I'm doing. D is 13 days long. E is what, 10 days long? And F is also 10 days long. G is 2 days long. H is 6 days long. I is down here, gotta be careful, 7. And J is 8 days long. Okay, now we are set up. We find the early start, early finish times by beginning at the starting node and noting that everybody here starts on 0 at the earliest. You could start right now. 0 is right now. Okay, so 0 plus 11, that means the earliest you could finish with task A is in 11 days, the earliest you could finish with task B is 10 days, and the earliest you could finish with task C is 8 days. Just common sense. Now we work our way through time, through the network. Okay, D can't start till A finishes. A could finish at the earliest in 11 days. That means D, just pass it over. Don't give anybody any time off. D could start at the earliest in 11 days. 11 plus 13 is 24. So this task D could finish up at the earliest in 24 days. Here's some easy passing as well. B, E, F, and G are all waiting on B, and B could finish at the earliest in 10 days. That means that they could each start at the earliest in 10 days. It's the earliest we could hope for. 10 plus 10 is 20. 10 plus 10 is 20. And 10 plus 2 is 12. G could finish at the earliest 12 days from now. H can't start until C finishes, so take that number and pass it forward. H could start in 8 days. 8 plus 6 is it could finish at the earliest in 14 days. I only have 2 more to do here. They're just a little bit trickier, but not if I picture it. Look at, for instance, I. Okay, I cannot start until G and H finish. G will finish at the earliest in 12 days. H will finish at the earliest in 14 days. It can't start till they're both done, so it's the bigger one that wins. You choose the larger. It could start at the earliest in 14 days. 14 plus 7 is 21, right? So it could finish at the earliest 21 days from now. And that we just did there, that logic that we just did there, we remember, that is called the early start time rule. The early start time of an activity is equal to the largest of the early finish times of those activities that immediately precede it. I think it's easier to just picture what we're doing, but you could memorize the rule. All right, we need to apply it again. Okay, because J cannot start until D and E finish, we pick the larger of their finish times. It's waiting on both of them. It could start at the latest in 24 days. 24 plus 8 means that it could finish at the latest in 32 days. And we say at this point, we could actually answer that next question because it asked how much time does it take to complete this project, and we are poised to actually answer that particular question. What is the completion time of this project? Well, we complete it here at the finish. How do we find that out? Trace anything that's connected to the finish and see when's the earliest it could finish. This could finish at the earliest in 32 days, that could finish at the earliest in 20, and this could finish in the earliest in 21. It's kind of like the opposite of a race. Who came in last place? Pick the largest. We would be waiting on J there at the end. And it would be done in 32 days. A project is not finished until all the tasks are finished. J would be the last one to finish up in 32 days. Oh, that's the answer to that question right there. Okay, now, if the questions stopped at this point, we wouldn't need to fill in the bottom side of the box. Those are the late start, late finish times. We only need that information if there's a question about late start, late finish of some activity. Yes, I didn't see it on the page. If it's a question about the critical path, because that reveals the critical path. Didn't see any question like that. Or if there is a question about the slack associated with any one of the activities. That is what that fourth question is. What is the slack associated with G? This is going to obligate us to finish the analysis. All right, late start, late finish times. We begin with this fact. We could finish in 32 days. We're going to finish in 32 days. 32 days is our deadline. That means anybody connected to the end must be finished at the latest in 32 days. Now we back up through time. Okay, so simple arithmetic. 32 minus 8 means that we have to at the latest start J in 24 days, because if we don't, we'll create a problem. 32 minus 10, we have to start F at the latest in 22 days. If we don't, there'll be a problem. 32 minus 7, let me do that right, is what, 25? We have to start I at the latest in 25 days. Now, we continue backing up. All right, well, I can't start, I'm pointing at it, so we'll work on it. Has to start at the latest in 25 days, and it can't start until these two things are finished. Okay, that means that that number becomes their deadline. G has to finish in 25 days. H has to finish in 25 days. Then just simple arithmetic, 25 minus 2, okay, that's what, 23? G has to start at the latest 23 days from now, or there'll be a problem. 25 minus 6 is 19 for H. H has to start at the latest in 19 days. It's similar up here. We discovered that J has to start at the latest in 24 days. That means that the two things that precede it have to finish at the latest in 24 days. 24 minus 13 is 11 for late start time of D. 24 minus 10 is 14 as a late start time for E. And we just keep trying to fill these in. Oh, here's an easy one. We can just pass the number. H can't start till C finishes. It's got to start at the latest in 19 days. That is C's deadline. It has to finish at the latest in 19 days. 19 minus 8 is 11. C could start at latest 11 days from now. And up here is another easy one. This 11, the late start time for D, becomes that 11, the late finish time for A, the only thing it's waiting on. 11 minus 11 is 0. Oh, I am really glad to see that. By the time you're done with this arithmetic, somebody attached to the starting network, at least one activity has to zero out. The late start time has to be 0 as well. If it isn't, then we did something wrong. Anyway, we're not done till we fill in this one, and this is the only one that's just a little tricky. Okay, because E cannot start until B finishes, F can't start until B finishes, and G can't start until B finishes. All right, now E has to start at the latest 14 days from now, F has to start at the latest 22 days from now, and G 23 days from now, and we do not want to delay any of these. That means that what is B's deadline in order to not create a delay? Here you do the opposite. You pick the smallest. You don't want to upset anybody. So B has to finish at the latest 14 days from now. 14 minus 10 means that it's got to get started at the latest 4 days from now to not upset this promise of being done in 32 days. And that was the so-called late finish time rule. The late finish time of an activity is equal to the smallest of the late start times of all activities that immediately succeed it or coming after it. Okay. Anyway, we were trying to answer a question about slack. And slack is just the difference between either the late start and early start time of a task or the late finish time and early finish time of that same task. You should get the same answer in both cases, so it doesn't matter which pair you use. They were asking about G. So I am zooming in here. The late start time is 25, right? The early start time is 12. The difference is 13. Yep, there you go. That's the answer to that question, 13 days. Oh, so actually, in terms of efficiency on an exam, we only really needed to fill out enough of the network to get to here to do G. But just for good practice, I went ahead and I did the whole network and filled out all the late start, late finish times. Okay, now, what's next? Oh, good, something visual, something interpretational. Your company has assigned you to supervise a project that consists of 6 tasks, A through F. Someone else in the company has determined the timing of the tasks and has provided this information for you in the form of a Gantt chart below. So this is all figured out. This is exactly when they're going to be doing each of these tasks. Each column in the Gantt chart represents 1 day, so that's important for interpreting it. Which of the following statements are true based on this Gantt chart? Okay, take them one at a time. Task F is the longest task in this project. Task F, where is it? It's right here. The longest task in the project. Well, how long is it? Each column is a day. 1, 2, 3, 4, 5. It's 5 days long. Is that the longest one in the whole project? No. Isn't B 1, 2, 3, 4, 5, 6? That's false. Only one task will be worked on during the first day of the project. Okay, each column is a day, and this is a timeline on a Gantt chart. That's the first day. I see that only A is going to be worked on. The entire time you're working on task E, you will also be working on task F. Task E is here. These 3 days apparently we're working on it, and I noticed that yes, that's true. Over those same 3 days we'd also be working on F, so that is true. So we have 2 and 3 is what tests true. That's partial credit. That's partial credit. Oh, okay. Oh, wait a minute. This last question is not about the Gantt chart, though. It's a whole nother question by itself. Let's look. A certain office building must be renovated and then sold. Okay. Renovation of similar buildings has taken an average of 4 weeks. Okay, I bet this is going to be important. An average of 4 weeks and a standard deviation of 1 week. Once placed on the market after renovation, buildings like this take an average of 10 weeks to sell with a standard deviation of 2. If the renovation started right now, which of the following is closest to the probability this office building will be sold within the next 15 weeks? The key to this question is recognizing what it is. It is a tiny PERT problem. Remember, we were working on a CPM problem earlier. Now I said, oh, this is a PERT problem, a very tiny PERT problem. And you might be looking at that and going, I don't see how that's a PERT problem, because PERT problems have that business about an optimistic time, a most likely time, and a pessimistic time. Yes, true, they do. But in this problem, apparently that's already been processed. Remember how we stick those into a formula and we come up with an average or an expected time and a standard deviation in the time that we anticipate that a particular activity is going to take. You know what? Maybe it helps to draw it. This is a project renovated and then sold that has 2 activities. One of them is renovate. You have to do that first, and then you have to put it on the market. I'm just going to write sell, right, for it to be sold. We're being asked how long what's the probability to be sold within the next 15 weeks. That is the length of the project. At the end here, it's sold, right? Here's your start, here's your finish. Oh, all right. Now, notice this. Renovation of similar buildings has taken an average of 4 weeks. That's essentially the expected time. I'm just going to write a little mu there because I'm lazy. 1 symbol for an average. But generally, you expect the average is 4 weeks. I might as well jot down that other piece of information I was given. The standard deviation is 1 week. And then selling, what does it say about selling? An average of 10 weeks. And a standard deviation of 2. Okay, now I know that the question said something about 15 weeks, but working towards that answer. A intermediate question is just common sense. So what's on average, how long do you think this would take? If it takes on average 4 weeks to renovate and on average 10 weeks to sell, on average how long do you think it's going to take to get this thing sold? Well, 4 plus 10 is 14. 14, the expected completion time of the project. This project only has 1 task, or excuse me, not 1 task, it's 2 tasks. It only has 1 path. Okay, you add up the times along that path. That's your done expected completion time. 14 weeks. Right. 14 weeks is the expected time. They're asking what's the chance it's going to be sold in 15 weeks. That's because we expect there's going to be some wobbling or variation around what we actually observe in this estimate of 14 weeks. They say, well, on average it's 14 weeks. Sometimes it's less, sometimes it's more. And in order to gauge how safe is 15 weeks, right, which is a little further down the line here, I need to know, well, how much is that wobble? What is the variance or the standard deviation in that particular curve that represents the project? Well, I do have the standard deviation in the 2 activities. And I remember in a PERT problem, oh, right, you have to do a z-score for each path through the project. Happy thing here, there's only 1 path. I have to do a z-score for just this 1 path to answer this question. You know, z equals the number I'm interested in minus mu, this one, divided by the standard deviation, that one, for the whole project. Okay, well, 15 is the number I'm interested in. We were just remarking that the expected completion time of the project is 14. Yeah, the problem is we don't know what to put in here. We have 2 different things here. We have to remember that, yeah, right, you know, when you were doing a z-score for a path, where did the standard deviation in the path come from? The variance in a path, variance. The variance in a path is equal to the sum of the variances along that path. The variance in a path is equal to the sum of the variances along that path. Wait a minute, the variance is the square of the standard deviation. So the variance in this particular task, renovate, is 1, because 1 squared is 1, but the variance on the market selling it is 2 squared or 4. The variance in the path, this sequence, is that plus that. Oh, all right, so the variance here is 5. You say, great, all right, I put a 5 there. Okay, in the z-score, you always need a standard deviation, which is to say, close, but be careful, put the square root of 5. Put the square root of 5, that gets you the standard deviation in the path. You say, why are you making this so complicated? I had 2 little standard deviations and now I need a big one. They're combined effect, right? Why don't I just add them? You cannot add standard deviations. You can only add variances. Just find the variances, add them together. That's then not exactly what I need for the big z-score. Take the square root of that and put it in the z-score. Anyway, when you do that, where's my scratch work? We get something like, oh, you have to, I rounded 0.45. It's a little messier than that, right? That's the z-score. What am I supposed to do with that, and why in particular did I round it to do two decimal places? Because I want to look it up on the z-table. The probability that the building will be sold in 15 weeks is the amount of this curve that represents everything that could possibly happen that is actually safely to the left of 15 weeks, meaning that amount of time or less. In computing this particular z-score, I took this very custom normal distribution and I translated it to a standard normal distribution because z is the number I'm interested in, right? See where it's shaded? It's telling me how much of the curve is behind that. 0.4, I just have to find 0.45. 0.4, that's the row. Third digit, 5, that's the column. I'm looking at 0.6736. 0.6736. I have to remember that. 0.6736. 0.6736. That's how much is in here. Oh, cool, wait a minute, and that is actually exactly what they're asking for, right? Probability of being sold. Oh, which is to say 0.6736 is 67%.